Okay, so we're at our part 2 video for chapter 2 on chemistry and biology, picking back up with electronegativity. So electronegativity is, the easiest way I know to describe it is how, um, how much pull or how much attraction an atom has for an electron. Okay, so a more electronegative atom will pull electrons, shared electrons, more closely towards it. It's not the same thing as, but if you were a satellite floating in space and you came across two planets that were relatively close together, and they had very similar pulls on you, on your satellite form, but you were a little bit closer to one planet than you were to the other. You were shared between both planets. You didn't fully belong to one or the other, but you were a little bit closer to one than the other because it had more pull. You can think of electronegativity kind of like that. Um, Again, not an exact point, but certainly will help you a little bit with the understanding. Um, when we talk about covalent bonds, we've been talking about sharing the electrons. But the question now that we know about electronegativity is do they share them equally or unequally? Is somebody stronger and more electronegative, or are they equal in their attraction for the electron? And so that's our difference between polar and and nonpolar covalent bonds. In nonpolar covalent bonds, those electrons are shared equally. They are equidistant from both of those nuclei. They're shared equally. The electronegativities are the same, and that is why it's called a nonpolar covalent bond. The opposite of that is a polar covalent bond. So in a polar covalent bond, one atom is more electronegative, and therefore the electrons are closer to it, and they aren't shared equally with the other atom. So this unequal sharing of electrons causes partial charges. It's not a full, I've stolen your electron and now I have an extra electron and I'm fully negative. No. What it means is the electron is just a little bit closer to this atom and therefore it's partially negative. So in this image, what you can see is you can see water. This is a water molecule. The oxygen is more electronegative than the hydrogen. And what that means is when the hydrogen shares one of its electrons and the oxygen shares one of its electrons, right, because this is sharing, what ends up happening is those electrons tend to be just a tiny bit closer to oxygen. Now, hydrogen's still happy because it has filled its valence shell. It now has 2 electrons zipping around in its outer orbital, and that makes it very, very happy. It's just that they're a little bit closer to oxygen than they were to hydrogen. That delta symbol that you see right here, the delta negative here, and then the delta positive here and here, see those? Okay, that delta is a Greek letter, and it's delta, D-E-L-T-A. Delta negative, delta positive. Those tell me that it's a partial charge. It's a partial positive or a partial negative charge. All right, so you've got a whiteboard activity. You've got this one, and then I'm going to give you answers. So go ahead and pause your video. I'll count to 5, and then I'll give you some answers. Okay, so molecules versus compounds, subatomic particle responsible for chemical bonds, covalent bonds, define it, and then a Venn diagram. If you're not familiar with Venn diagrams, you should be. They're a really great way to compare and contrast things. There are some great YouTube videos out there on how to make a Venn diagram if you haven't been exposed to that format. You can Google them. All sorts of things. So if you're not familiar with a Venn diagram and how you can use it to compare and contrast, or how you can use it to compare and contrast even more than 2 things, I'd go ahead and Google that and learn that skill set. So we've been talking about electrons and why they're important, and we said it's because of bonding. We've talked about covalent bonding, both polar and nonpolar, and that is the strongest bond that we're going to come across. Now we need to talk about ionic bonds. In ionic bonds, one atom gives up electrons and the other atom takes them. Okay, so electrons actually transfer. So we're going to use the example of table salt, where you're going to use sodium and chlorine. And what's going to happen is we're going to see a transfer. One of the electrons from sodium is actually going to leave the orbital, the valence shell of sodium, and it's actually going to be transferred into the valence shell of chlorine. Okay. The thing about ionic bonding, or when we transfer those electrons, is what this now means is that each of those atoms have charges. They're no longer neutral. They no longer have the same number of protons and protons and electrons. They now have either one more electron than proton, or they have one less, in this case, electron than proton. Anytime we come across that atom where they have a different number of protons and electrons, we call that an ion. Okay, so here's what I'm talking about. See sodium? Sodium has 2 electrons in its first shell, it has 8 electrons in its second shell, that's 10, and it has one lonely electron floating around out there in that outer energy shell. One very highly energized, very attractive, lonely little electron floating out there, and cool chlorine comes along and says, hey, check this out. We're perfect. I have one opening in my valence shell. I've got room for one more. This is exclusive. Send your electron over, sodium. I'll take good care of your electron. You'll have a stable valence shell because you'll no longer have one little electron floating out there. I'll have a stable valence shell because now I won't have 7, I'll have 8, and it'll be good. So what ends up happening is that's exactly what happens. That lonely electron moves from sodium over to chlorine, but now what that means is sodium has 11 protons and only 10 electrons. Because I have more positive proton charges than I have negative electron charges, sodium has a positive charge. It is a positive ion. On our next slide, you're going to see how this is spelled, but we're going to call that a cation. Chlorine also is an ion. They are both ions. In chlorine's case, chlorine now has 18 electrons. It previously only had 17. 2 in the first, 8 in the second. It had 7 in the third, but now it has 8. It has a stable valence shell. But what that means is it has 18 electrons and 17 protons. And so we have one more electron than proton, which means I have a negative charge. We call that an anion. So students over the years have told me how they remember this. They look at cation, they see the plus sign of the T, and they know that's a plus sign, and therefore cations are positively charged. Other students have told me, oh, that doesn't work for them, but they look at anion. And what they see is they see an A, an N, and then the word ion. They see A, N for negative, ion. A negative ion is negatively charged. No matter how you remember cations and anions, what you do also need to know is that because I have a positive and I have a negative between, right? So opposites attract. I have a single positive and a single negative. They're going to attract one another. And that attraction between the positive and the negative charges of the cation and the anion, that's what's going to form an ionic bond. So that's how I get an ionic bond. I'm not sharing electrons, I'm actually transferring them. And then the attraction between the positive and negative of the cation and the anion is what's going to give me an ionic bond. So I'll pause for 5. You pause your video. I'll be quiet for 5 seconds, and then we'll do the answers to these. Okay. So we've said all this. You'll notice that I ask you to use your sciencey words. That's me wanting to use you to use words like cation and anion and poles, right? And then if you don't get those, send me an email, talk to me in class if you're in my face-to-face, but let's make sure that you've got these concepts down. Okay, so we've talked about very, very strong bonds. Those are the covalent bonds. The next strongest bond on our list were the ionic bonds. Now we're going to talk about some weaker chemical reactions, or some weak bonds. And specifically, we're going to talk about hydrogen bonds. Okay, hydrogen bonds form when I have two molecules or two compounds that have covalent bonds within them. But because of the electronegativity, what's happened is I've created those partial charges, like when we talked about water, and we talked about the partial negative charge on the oxygen and the partial positive charge on the hydrogen. Well, now I have this partial positive, right? It's a little bit positive. And just by the nature of being that way, it's going to be attracted to something that's a little bit negative. Okay, so it's like an ionic bond, but not. Okay, it always involves hydrogen. Okay, and in every case, that hydrogen is going to have a partially positive charge, and what's going to happen is it's going to bond with, be attracted to something with a partial negative charge. In living cells, that's usually oxygen or nitrogen. It's one of those two typically. It can be something else, but because we're in biology, it's in what we're talking about, it's usually oxygen or nitrogen. So I'll stop chatting for 5, you'll work this out, and then I'll give you some answers. Okay, so your words don't have to match mine exactly ever on these. I just give you an answer because some of you find it helpful to know how I would answer it. Question 2 on here is hydrogen bond a strong bond? No. And here's how you know that. You know this. Envision a pail of water. Okay? Now push your hand into that water. How hard is it for you to push apart those water molecules, right? And push into that water? It's relatively easy. Think about some other liquids that are more viscous. It's harder. You have to put more force to push through that liquid, okay? By the same token, hydrogen bonds are weak. They'll break very, 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 very easily, but they'll also form very, 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 very easily. So that concept can be visualized by pulling your hand out of the bucket of water. You pull your hand out of the bucket of the water, how long does it take before that water fills in the space where you were? It's virtually instantaneous, yes? So very weak bonds, but they break and they reform very, very quickly. And that'll become important later when we talk about properties of water. The last one, the in your own words, again, doesn't need to match mine, and it really shouldn't. You shouldn't memorize my answer. You should come up with one of your own that makes sense. Textbook talks about van der Waal attractions, and we don't do a lot with them, other than I use them only to say that they are why geckos can walk vertically up walls. It's, part of the magic of Spider-Man, if you will. Sort of, not really. But van der Waals, very, very weak. These guys are the weakest of all the bonds that even get mentioned in the chapter. Okay, so molecular shape and function. We're going to touch on this from the aspect of function and shape are really, 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 really important to a molecule. And that becomes super important when we get to the macromolecules in chapter 4. So that's part of why we touch on it here. But a molecule's shape is determined by its atoms, the positioning of its valence electrons, how its valence orbitals fit together, and some can have very, very similar structures, but not be the same exact group of atoms or elements or molecules. So in this image, we have that interaction. And the shape is important because of interaction. You are a giant ball of chemical. You are matter. Everything is made up of matter. and atoms. Atoms make up everything. So how they're put together can influence, it does influence, it does influence how they function and what they do. So for instance, here's a biological molecules, and we can have interactions or cross reactions just based off of their physical shape. So there's a natural endorphin on the left, and on the right is morphine. And look at what's happening. So there's a receptor on this cell, that's that purple thing labeled an endorphin receptor, and it's designed to bind to this natural endorphin in an individual's brain. But look at morphine. Overall, they look nothing alike. Overall, they don't even have the same chemical composition. But this one little section of morphine has just the right shape that it can bind to that endorphin receptor, and it can release the same euphoria as natural endorphins. So that's the chemistry. That's this whole molecular shape influencing function. And that's important because of chemical reactions. So in a chemical reaction, we make or break a bond. Okay? So back here, that natural endorphin binding to that receptor, to that protein in the cell membrane, created a chemical reaction, a very specific chemical reaction. Now let's say I don't have enough of that natural endorphin, but what I do have is morphine. So we can use morphine to create the same change within the cell that we would if we had the natural endorphin, and we can do it without having to create that natural endorphin. Okay, so it's those chemical reactions that are so important. The molecules that start a chemical reaction are called reactants, and the end result of the chemical reaction, those molecules are called products. So here I have two H2 molecules. I have an O2 molecule. See that double bond between the O2, both of the oxygen? And what I get from here, those are my reactants, my hydrogens and my oxygens. And my products are that I get two water molecules. Okay, so here's the equation for photosynthesis. So in photosynthesis, we use sunlight, the energy of sunlight, and we convert water and carbon dioxide. And what we get back are glucose, that's your C6H12O6, and some oxygen. So in this, my reactants are the 6 carbon dioxide and the 6 water. My products are that compound of C6H12O6 and those 6 oxygen molecules. Okay. Another definition is chemical equilibrium. So sometimes chemical reactions go, all of reactants get converted into products, every last one. Sometimes, and then it stops. Sometimes those reactions are reversible. So I can be converting reactants into products, but just as quickly as I'm doing that, those products can be re-breaking down back into reactants. And it's kind of this circular sort of situation. Okay, so the reaction is reversible, and that's how we get to chemical equilibrium. Chemical equilibrium says that when the forward reaction and the reverse reaction rates are equal. So I'm making product just as fast as I'm breaking it down and turning it back into reactant. That's chemical equilibrium. Whiteboard. So go ahead, I'll pause, you'll write. And the answers. And I think that's going to be the end of our chapter. Let me just peek. So yes. So these are just images that I pulled from a textbook. I don't even know. I think it's Pearson. I think it says so on the bottom there. Just little things that I thought were helpful for students. And just Lewis dot structure, that kind of stuff. That sometimes gives student trouble. The Learning Resource Center is great at Lewis dot structures. You can schedule time, come to my office. You can drop by at any of the office hours. But I'm going to wrap up this video and get it loaded for you guys. Thanks.